Differential equations, we're in section 6.1, our second day, and we are working with power series solutions. Now, of course, many of these equations, differential equations, I should say, that you're going to look at, very well could be solved with earlier methods. It's always important to bring that up. But you're learning of a new method that can help you out when some of your previous methods are not applicable. So power series are incredibly powerful. They're going to really give you a wonderful way to attack some problems that otherwise you wouldn't be able to. Here's what we're going to do. We're going to assume that there is a solution, and we'll assume it's a power series centered around 0. And so there's some coefficient c sub n, and it can be different for each power of n. You can see that's like x minus 0 raised to the nth. And what would this look like? Well, if you plugged in a 0, you'd get c sub 0 x sub 0. Plus, well, plug in a 1, you get c sub 1 x to the first. C sub 2 x to the second. You get the idea. You know, this goes on for an infinite number of terms. Well, look, if we took our derivative, I just want to remind you, and this is something that we saw in BC calculus just as well, when your series is starting with a constant like this, you take your derivative, you lose that constant. And then as you take a derivative term by term by term, you'd have c sub 1 plus 2 c sub 2 x and so forth. We've talked about that in the past. Of course, what that really is going to do, you're going to lose that 0 term, and then you just go ahead and you take your derivative, and it's going to look just like so. And of course, if you really wanted to double check that, you could. You plug in a 1, you'd get c sub 1 times 1, and then that's x to the 1 minus 1, which is a 0. You plug in a 2, you'd get 2 c sub 2, and x to the 2 minus 1 is just an x. And you can see that's what you'd get term by term by term. For your second derivative, well, once again, now you're going to lose that constant out in front, and you'd always do that. So look at your counter drops by 1, and now you take your derivative, you're going to bring down one more power, and this is n minus 1. And then we'd have x to the n minus 2. And hey, that's great. That's where we're going. Now we're going to substitute these in. So we will have 4, but what do we have for our second derivative? Well, we can write that as a power series. And we're going to do that right here. We just did that a moment ago. And then we'd say plus y. Well, what's our y? Well, our y, we started off right there. It's also a power series. N equals 0 to infinity. C sub n times x to the n. And yeah, this can look very ugly and very frightful at first. Realize you could, of course, this is almost a very simple simple move right here where you just bring that 4 inside. Look at that. But here's where we're going to notice things aren't quite the way we like to see it. You're going to notice quickly now that as you're looking at your counters, one of them is at a 2, the other one is at a 0. And perhaps even more troubling, and this might be the most troubling issue, you can say now, paying attention to these powers of x, they're different. And my goodness, let's just do a reorganization. And this is really a great move that we're going to be doing repeatedly. Let's just say, wow, it sure would be good if that power of n minus 2 would just be called a k. Likewise, when we solve for n, of course, would be k plus 2. But we'd like to reorganize this series with x to the k. And you'd think, well, why? Why do you want to do that? Well, if you do the same thing over here, you're going to be able to really arrive at these two power series as simultaneously representing x to the same power, the power of k. What's the benefit? Well, then you'll be able to join them together. Look, if n's equal to 2, well, 2 minus 2 is 0. And I can say, well, let's just write that as k equals 0. Obviously, as n goes up to infinity, k is going up to infinity also. Look at this. We have c sub n, but n is really k plus 2. We have this n right up here. Well, that's going to be k plus 2. N minus 1 is going to be one step below that. You could subtract a minus 1 on both sides if you'd like and see that you'd get k plus 1, or you could just use common sense and say, hey, I see what's going on here. If I had the nth term as k plus 2, n minus 1 would be one step lower. But now what? You'll have this power of x to the k. Now this next one, the second series, is really just a cosmetic change, isn't it? Everywhere where you have an n, you just replace it with a k. And of course, right now you look at this, you'd say, well, did I really accomplish anything? My goodness, you did. Here's why. You should be thrilled to see this, because right now you've got x to the k for both of your series. Even better still, your counters at the bottom both are starting at k equals 0. Now, if not, if you'd have one of those down below would start at k equals 1, or a different counting value, starting value, then go to your other series and begin to plug in those values, and you'll separate it, you'll pull it out until you have the same starting k value for both. Look, what you can do right now, though, is you could say, hey, I'm going to turn these two into 1. And, of course, both of these have an x to the k. I'm going to factor that out, and we're going to be left with 4c sub k plus 2 times a k plus 2, k plus 1. And then we'll say plus c sub k. And of course, we've got x to the k out here. And this is a wonderful step right here where you can hopefully notice, look at this right-hand side. No matter what you have for a power of x, there's a 0 in front of it. So you know what you're really saying is this thing right here has to equal 0. Why? Well, the right-hand side, what's in front of x to the third? A 0. What's in front of x to the first? Well, a 0. So very quickly, we'll have 4c sub k plus 2. Here's k plus 2. Here's k plus 1. Set that, adding c sub k, set that equal to 0. What we've been doing, guys, is we've been solving for the higher counter. We're going to get that all alone, and this really just becomes an Algebra 1 problem. So we're going to solve for c sub k plus 2. What's going to happen? Well, this c sub k is going to move to the right. That's a negative c sub k. And then all of this stuff over here, we're going to divide by a 4, by a k plus 2, and also a k plus 1. And look at that right there. We are well on our way. We have a way to express the one coefficient in terms of another. So here's where we can do a little bit of work. I'm going to say, hey, let's look at what happens when k equals 0. Remember, k is a counter, and we can say, what exactly are we getting? Well, we would get c sub 2, because 0 plus 2. Up on top, we'd get negative c sub 0. And down below, 0 plus 2 is a 2, 0 plus 1 is a 1. 1 times 2 times 4, hey, that's just an 8. And then, guys, we're just going to iterate. We're just going to keep plugging in the next higher value of k. So, if k is equal to 1, we'd have c sub 3. And our numerator would be negative c sub 1. But down below now, well, we'd have a 1 plus 2 right here. That becomes a 3. 1 plus 1 is a 2. 2 times 3 is 6. 6 times 4, you'll get 24. Okay, and then what? You just keep going. Say, let's see what happens with k equals 2. With k equals 2, you'd have c sub 4, right? And then up here, we're going to have negative c sub 2. And down below, 2 plus 2 in this parenthesis is a 4. 2 plus 1 is a 3. And a 4 times 4 is 16. 16 times 3 is 48. However, this is where you really want to pay some attention. You're going to say, now, wait a minute. Look at this c sub 2. I can go ahead and substitute that in there. That's so important. We're going to do that so much. We're going to say here's our negative. Well, that's negative c sub 0 over 8 all over 48. Well, a negative and a negative make a positive, don't they? And then what is 8 times 48? Well, I hope you would agree with me. That's going to be 384. 384. You can do that very quickly, right? All right, so let's maybe do one more step here, get k equals 3. And by the way, you could go as far as you want. K equals 3, we're going to have c sub 5. That means we'll have a negative c sub 3. And down below, these numbers are going to get a little bit bigger. Remember, we'll have a 3. 3 plus 2, this becomes a 5. 3 plus 1 is a 4. And 4 times 5 is 20. 20 times 4 is 80. So it doesn't take too much work. But here we go again, with this c sub 3. C sub 3 is going to be right over here, isn't it? It's going to be negative c sub 1 over 24. And down below, we've got our 80. Once again, a negative and a negative make a positive. So we'd get a positive c sub 1. And then 80 times 24, well, we'll have a 0 here, and we'll just multiply through. That should be 1,920. Okay? So right now, we're well on our way. We're doing great. We just have to go ahead and see where this is all coming together. We know we've got a general solution, right? We've got this, n equals 0 to infinity. Here's our power series. And what does that really look like? Well, it's c sub 0 plus c sub 1x plus c sub 2x squared plus c sub 3x cubed plus c sub 4x to the 4th plus c sub 5x to the 5th. Going on forever, right? But now you know what? We know what these values are equal to. What was c sub 1? Well, you didn't see that right there. We really started at c sub 2. We'd say c sub 2 is negative c sub 0 over 8x squared. That's from that iteration work up there. C sub 3, well, you could see that's going to be negative c sub 1 over 24 x to the 3rd. How about c sub 4? Well, you can see that's going to be c sub 0 over 384 x to the 4th. The last bit of work that we did right here, c sub 5, was c sub 1 over 1920, and that's x to the 5th. And of course, this is going to go on. But I guess what I really want you to notice is this. You're going to notice that half of these terms involve the constant c sub 0. Likewise, you're going to notice that the other half of them involve the constant c sub 1. And that means that we could write very quickly now that, y sub 1 right here, would be, with c sub 0 in yellow, c sub 0 minus c sub 0 over 8x squared plus c sub 0 over 384 x to the 4th. You can see just copying everything that we had highlighted in yellow. In green, well, we've got c sub 1x, pardon me, we'll say minus, gotta get this eraser working, minus c sub 1 over 24x to the third